Okay, so the first thing that we're going to do is that we are going to contextualize the algorithm. We are going to see, we're going to talk about why the algorithm is important. We always start with a question, right? What is the question that we want to answer with this algorithm? What is the problem the algorithm is trying to solve? The question is, how can we find a value in a set of values? I'm saying set, I'm using the word set loosely here, just in a bunch of values. That is the answer that we want. That's the question that we want to answer, right? So now, let's say we have a whole bunch of values. We have an array. Let's say, how many of you know what an array is? And I am not looking at the chat right now, so I won't be able to see the answers in the chat. So you, Christine, you tell me what they're saying.
Hey guys, so who knows what an array is? So Diana raises her hand. She knows what an array is.
I think I know.
Okay.
Do you know what an array is?
So what is an array?
Yes.
So let's say this is an array. And what is an array? An array is simply a block in memory that has a whole bunch of buckets. Each one of these buckets is a container that's going to hold some value. Usually when we start talking about this algorithm, we use integers because it's easy to think about them in terms of where they are and comparing them to see if one is greater than the other. So we're going to use integers. Let's say we have this array of integers and we have values. Each one of these buckets has a value. And there's something that we're going to learn. When we talk about algorithms, we talk about preconditions. We talk about preconditions. Precondition is something that has our data has to meet for this algorithm to work. Okay, so the one precondition for this algorithm is that the values in this array that we have here, it has to be sorted. Otherwise, it doesn't work. So I'm going to write the data sorted. I'm going to say 2, this has a 4, we're going to have 5 here, and 8, and 10. I'm just making stuff up. 14, I'm going to say 18, I'm going to say this is a 20 here, 21, a 22. Then we're going to go all the way to 30, and then 40, and then we're going to say 41, and then we're going to say 44, and then I'm going to say 45, and then I'm going to say 50, and then 60. I don't know. I'm just making stuff up. So how can we find a value in a set of values? One option is we could start looking, we could start from here. We could start there. And we could start looking at each one of these values and see, is that, let's say I am going to, somebody gives me a value. I'm going to look for, I'm going to pick 21. I'm going to look for 21. I could start here and I could say, is this 21? No, it isn't. Is this 21? No, it isn't. Is this one? No. And then I'll go all the way until I find it, right? And then I found 21. So I went, I'm gonna write the indexes here. And as you might know, indexes in arrays start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Okay, so on bucket number 9, I found 21. To get here, I had to check 10 values from 2 to 21, and then I found it, right? So the worst case scenario, if I'm looking through the array sequentially, is that I don't find the value. Let's say I'm looking for 48. I go and I check each one of these buckets, and then I don't find it. And I checked 18 places just to find out that my value is not there. Now, how do we make this more efficient?
Does anyone have any suggestions? Can anyone think about how they might try to make this more efficient? Okay, nice. Diana says if it's sorted, go in the middle.
And
then left or right.
Okay. So the idea of the binary search, she is correct. We
Good
know.
job, Diana. Oh, I just said good job, Diana. That's all.
Yeah. Thanks for the help. So the idea is that if we know the array is sorted, we can look in the middle of this from 0 to 70. How do we find the middle? How do we find what the middle is in this array?
Does anyone have a guess about how we would find the middle of an array? Diana says division using length.
Using the length. Okay. The length of this array is 18.
Ooh, and then Kieran says you can divide the length of the array by 2. And also, feel free, guys. You can also unmute yourselves. It's totally a conversation here.
Yeah, it's a conversation. So 18 over 2, that is 9. So this will be the middle, is it? It is the middle. So I have 8 to one side, and I have 9. Yeah, I have 9 to the other side. Can this be considered the middle? What other options do we have? Any other ideas? What about, we have, this is bucket number 7. This is bucket number 0. So 17 minus 0 will give us 17. If we divide this over 2, that gives us, what's the value there? That's 8, right? 8.5. 8 is what would be considered the floor. So let me write that exactly. So I'm gonna take the floor of 17 minus 0 over 2, and this is 8. We could take the ceiling, which would be 9, or we could take the floor, which is 8. Either one of those would work. But anyway, so let's check the middle. Which value were we looking for? We were looking for 48, I think.
Mm-hmm.
So we say, is this 48? It is not. It's not 48. So then we ask ourselves, is 48 smaller or, oh gosh.
It's so hard to write text on the whiteboard.
Yeah, smaller or greater than 20. It's greater, right? So since we know this is sorted, we know we are not going to find it here. So we just cross this whole thing over. Let me see. I'm going to change it to red. So we just cross this whole thing over. We don't need to look in here. We know it's not there. We're going to look in this section, right? So now we're going to start looking from here. And I'm going to change the colors. I'm going to start looking from here to here. We're partitioning, we are dividing the problem. This is called divide and conquer. Divide and conquer type of algorithm. So now we're going to look in the middle of this array. How do we get the middle again? Again, we take the floor of the last bucket minus the first one in the set, which is 9, and we divide it in 2, and that gives us what's the result here? Somebody help me. No? Can't hear anything.
17. Okay, so 17 minus 9 is
that is
divided by 2 is 4.
So now this is the that is 4. So it's gonna be actually the first one minus plus 4. So that's 9 plus 4. How can we make this better? Yeah, 9 plus 4 is 13. So that's the value that we're gonna check. This is the middle. Is there another way we can check this?
It should be 17 plus 9, right? Not 17 minus 9.
Yes, that is, you are correct. Yeah, because this is taking the difference in the set. It should be plus, and the same thing here.
Good catch, Rahil.
Thank you. So where is the? So that is 26 over 2, and that gives us 13. So we check 13, and then again we decide, is 48 here? It is not. And again, it's 48 is greater than 41, so we keep on moving, and then we discard all this. And then again, we're gonna start looking from here to here now. And again, we do the same thing. We take the floor, floor of 17 plus 14 over 2. And that gives us 31 over 2, and that is 16. Well, 15 actually is the floor. So this is the middle. And is it 48? It is not again. So then we discard this side, and now we look in here. We do the same thing. 17 plus 16 over 2, and that is, this is 33 over 2, and that is 15, 32, that is 16. So it's this one here. And now we see, okay, 48, it's not here, right? And there's nothing below. There's nothing down here, back here. So we know now this value is not there. So we know it's not in the set. And we checked 1, 2, 3, 4 times, instead of checking the whole set, or at least 15 if we're being, or 16 if we're being smarter with the other sequential search. Now, why is this important? Why is this algorithm much better than searching sequentially? When you notice, every time you look, you eliminate half of the set. Every time you look, you eliminate half. Every time you look, you eliminate 1/2. Meaning, if you have 2 elements, if you just have 2 or an array of 2, these 2 and 4. If you have this, how many times are you going to check the array? To see if the value is there or not.
Diana says one time.
Usually, you would check. You would check the middle, and usually will fall either here, probably fall here. If it's there, it's there. If not, you still have to check this, right? So twice, that much. But most of the time, it will be only once. If the array has 4 elements in it, if it's 5 and 8, you're gonna check again. You're gonna check here, and you're gonna know this is once. You're gonna eliminate this, and then you're gonna check again in here. And if it's there, it's there. Otherwise, you can eliminate this. In this case, I am using even numbers, and it's hard to work with even numbers. But if it's uneven, you basically eliminate half of it, and you can look in the other. But the most you will check is 3 times. If you have 8, the most you will check is 4 times, and you will realize when you have 2 values, you check, and ideally will be once. If you have 4, 2. If you have 8, 3. If you have 16 values, because you eliminate half of it, you just have to check 1 more time, 4. And it goes like this. So 32, 5, right? And you realize that this is 2 to the 0. This is 2 to the 1. Sorry, 2 to the 1 to the 2. This is 2 to the 3. I mean, this value here, right?
Diana says, is this log n?
This is log n. This is 2 to the 5. This value here, and I should probably write the values on the other end. It's just I didn't plan for this. So this is 2 to the 1. This is 2 to the 2. This is 2 to the 3. This is 2 to the 4. This is 2 to the 5. So let's say if we have a value, what is 2 to the 10? Can somebody tell me what 2 to the 10 is? I think I have a calculator.
1024.
1024. Okay. So this is 1024, right? So if you have an array that has 1024 elements, and this is usually, this is plus 1 because of this unevenness and whatnot. But if you have 1024 elements in an array, you will check almost 10 plus 1 times to either find the value or find out that it's not there at most. You won't have to check 1024 values, right? Which is what you would do in a sequential search. That is why this is important. And you see, if we double this, this is 2 to 11. We just check one more time. And if we double this, what is the value? 496, right? This is 2 to 12. So you see what's happening there? The number of elements are doubling, but the number of checks that we need to do to find a value it's just once. It's just one more time. Because every single time we go through here, we can eliminate half of the values to look for. That is why this is why binary search is a big deal.
Is the +1, is the reason why it's +1 because it always has to check once to make sure, like it's like to make sure that the element is the correct element that we're looking for or not the correct element we're looking for?
Yeah, let's say we have 2 and 4, right? And let's say I'm looking for number 6. Or let's say I'm looking for number 3. It's not there. I check here. And I say, oh, 3 should be after me, right? I have just 2 elements to check. So I still have to check here because 3 could be here, but it's not. Once I check here and I know it's not there, I eliminate this option. But I still have to check in the other option. And that is, that I still have to check here. If I know, oh, it's not here, there is nothing after me, and I am the only option, then it's not there, right? But usually, and it's this is usual for even numbers. For odd numbers, it will be like if this were 3, then you only check twice, right? But anyways, it doesn't matter. The point is that every time the values double, you only have to check one more time. Now, how do you implement that algorithm? Do you want to? Do you have any questions, first of all?
Does anyone have any questions? Is this making sense to everybody about the range and how we're having the range and how the number of checks goes up, but not as much as the number of elements because it's a log n algorithm?
This is log n. And what is log of n? what is the logarithm? That's a good question, right? What is a logarithm? What is this? Does anybody have an answer for that? Let me look at the chat. It's the reverse of an exponent. Yes. So a logarithm, and this is logarithm of base 2, by the way. So a logarithm is, let's say, if we have a value, we have 10 to the power of 2, and that is 100, right? So the logarithm, since it's the inverse of this, we're going to say the logarithm of base 10 of 100 is 2. It's to the power of what I need to elevate the base to get this value, right? If we have 10 to the power of 3, that is 1,000. And I'm using base 10 because it's easy.
I wish that I had learned math using metric number. You know, I feel like it makes. I feel like
yeah,
it's using
easier,
base
right?
10 is easier. Yeah.
Yeah. So yeah, that's 3. Now, why do we use base 2 here? It's because of this word, right? It's a binary search. It divides it in half, so that makes it so it's every time doubles, which is logarithm of base 2. We just have to increase it once, which is in this case, if we have 2 to the power of 4, we know that it's 16. Then logarithm of base 2 of 16 is 4, right? Anyway, so that is what the logarithm is, and this is the reason why it's big O of log n. That's why this algorithm is big O of log n, because every time, and this is, to be more precise, base 2 of n, right? It's because of this, because the numbers are doubling, because every time you elevate 2 to the power of 1 plus the one before, the number of the value doubles, right? Does that make sense? Okay, are we ready to implement it?
Raise your hand or speak up if you're ready to
Yes, please.
implement.
Applicable only, please.
Oh, okay. Okay.
No more of this crazy theory.
Yeah, but it's important, and this is and you will see, you know. Oh wow, I left this open. That's something I was doing before. New file. I'm just going to create a new file here, and then this is. I am going to IPYNB. What? Let me close this. I think I have another. What? That is not the one I want. Sorry, guys. I'm just, where did I left that? So many things. North Europe always. Okay, this should be good. As I said, I wasn't prepared. I went out to get a haircut, and that took really long. And what I learned is that a lot of there's a shortage of hairstylists because nobody wants to come back to work because of COVID, apparently. And so I am going to move this up here.
You know, that makes sense, not just for hairstylists, but I feel like whenever I leave the house, it's like, you know, because then you have a bunch of unknown factors that are gonna, you know, come into play.
Yeah, right. How can I escape this? God, this is the first time I use this. So anyways, I'll just leave it there in the background.
That works really well, the whiteboard.
So we are going to implement a binary search in Python because I haven't really looked for how to do it in Java yet, but I promise I will do it. So when we want to find an element in an array, right? And we are going to look inside an array. So I give my function, and I say, I'm telling Python that I want to find a value in an array, and then I'm going to pass in the target. Give it an array and the target. Now, we said that we want to look in the middle, right? And we're going to keep on cutting the array in half every single time. There are two ways of doing this. There is an iterative approach, and there is a recursive approach. I am going to do the iterative approach, right? Usually, I like to use left and right. A lot of people use low and high. What do you prefer for the values in the array?
I think, okay, Kahal says left and right. I mean,
left and right.
Let's try that one. And also, Diana has a question.
Yes.
That we can tackle either now or later. But can you explain how the log notation changes based on how many times we go through the array?
The log notation changes based on how many times. What does that mean? As in time space. Okay. Okay. We'll do that. Usually, remember how we started, right? We started looking at the 0th element and the 17th element, which are the two greatest, and we look in the middle of those, right? So I'm going to do the same here. I'm going to set left to 0, and I'm going to set right to this is how you get the length of an array in Python. And that's going to be because it starts at 0. That's going to be 1 greater than the last element, right? And then what we're going to do here, you see how we're cutting everything in half, and then we're moving to the next one, right? If I'm looking in the one to the right, I am moving my starting point, my left pointer, to the next one. And I keep on doing that. Move to the next one. And the same thing will happen if it will be before, but I will move my right, this pointer, I will move my right pointer to the one before me. And that I basically eliminate half of the array that way. So I'm going to do the same in my algorithm. I'm going to be moving, and we're going to see some interesting things. So what I'm going to say is, like, I'm going to say while, and this is because I'm going to keep on looking in the array while I haven't found the element, or if I'm there, I still have elements in there. How do I know if I still have elements to search? If my left is less or equal than my right, right? My left pointer, my left pointer has to be less this value here than my right. What happens here when I check 50 and I couldn't find, let's see, I couldn't find 48 because it's before. And I just have two elements. This is just one element. I eliminate this basically by doing that. And then I move my right pointer to here, right? Instead of being 17, I'm saying, oh, I'm going to look back here. So I'm going to move my right pointer to the one before me. So now this is left and this is right. So now right is less than left. That means there is nothing here. Like I run out of room. The element is not there. Like I won't find it, right? So that's exactly what we're checking for in here. If less, and I'm saying less or equal because there could be a point where they are pointing to the same element. Let's say if we have 3 instead of 2, and while you're looking, you end up with having one odd element in the middle, and both are pointing to the same. This accounts for that. And then here, inside here, I'm going to ask myself, is the target element before or after the middle? I haven't calculated the middle yet, but that's what I'm going to ask myself. And the target. And if that is the case, I am going to move my right pointer to the right of what left is pointing to. So I'm going to say the right pointer is going to be the left minus 1. Is that correct? No. If I am, if it's before me, it's going to be the middle minus 1. That's why it didn't make sense, right? Because I'm looking at the middle. Let's calculate the middle first. So the middle, we said, is whatever right, the value of right is, plus the left divided by 2. And this is an interesting thing in Python. Python 3 at least, the regular division does the normal floating point division, and the double slashes does an integer division. And an integer division gives you the floor. You know how this would be 15.5? So the regular division, this will give you 15.5. But this will give you 15. It will give you the floor. So which is what we need. So if the target is before, right, then we move the right pointer to before. I'm checking the middle. So then I will move the right pointer to here, right? Then L, I think it's L if the target is greater than the middle, which is the case, don't forget the D, which is the case we were looking in here, 48. We were looking at 20. It's greater. So then I will move this left that was here. This was left right here. I'm going to move this all the way to here. So now left is this. And this is the middle. So it's just basically 1 after the middle. So our left is going to be middle plus 1. Right? And then what is the other case in here? It could be before. It could be after.
What happens if the target's right in the middle?
We return the index. Oh, and that's one thing, right? This is I'm going to comment this. Return the index, the position. Okay, I'm going. This is the index. This is the position. This is where we're looking. So if it's not before and it's not after, well, it's the middle, right? Does that make sense? Now, what happens if we look through all the loop goes on and on and on, and it never returns? What does that mean?
Diana said not found.
It's not found. And what are we going to return if it's not found? What are we going to return? Any ideas in the chat? It is not found. Yeah, it is not found. Yeah. Why do we return -1?
Kahal, do you know why we return -1?
Any ideas why?
Diana says the index -1 doesn't exist.
Exactly. That's why. So we return -1 because we know that -1 is not an index in the array. So we will never confuse that value with an index. Now I know that in the class what's the class 243? 243. You were asked to return where that value will go, right? If it's not found. right? How would you do that? How would you modify this so it returns the position where that value would go? Any ideas? No? Huh, no idea. Okay, let's think about it. And I don't know. I just thought of it right now. I just remember. So when we know that after this while loop, right is less than left. That is because that is the condition. So at this point, right is, that's not the way you comment thing in Python. Left is greater than right at this point. Can we use that? No, we cannot use that because it could be because of this or because of this. So we don't know if it goes after or before. So what about we keep track of that? What about declaring a variable in here? Let's say is after. And this is going to be a Boolean. Okay? And I'm going to initialize to false. False is uppercase in Python. How does that sound? How could I use that? So I can say, like, it's after in here.
Are you creating this as a flag?
I'm creating this as a flag, and I don't know. So here's the thing, right? I'm possible position. I don't know. And then I could initialize it to the number. Could this work? Let's say if I look in here, if it's less than the middle, so the possible position is it would be the right. If it's greater than the middle, possible position is the left, right? And I'm just probably not the best name for that. So what I'm thinking is that this, if it returns the middle, it doesn't matter. That this variable doesn't really matter. But if we go through, right? If we go through all this possible position would hold the value of either what left move onto. Let's take this case, this example. So 48, we didn't find 48 here, right? 48 was not there. If 48 were in the set, it would be before 50. And then that's why we move the right pointer to here. But then that right pointer becomes less than the left pointer, and then we get out of the loop. Now, our possible position will be pointing to this. Oh my God. Okay, let's say this says let's assume this says possible position. Just imagine that. So the possible position would be right after the 15, right? Would actually be 16. Yeah. So my logic is flawed. Possible position in here could actually be one after. It would be middle plus 1 to the other side. And here would be middle minus 1, because I'll be inserting it after. So let's say, what if, let's say I'm just assuming, in our example right here, we're looking for a 3. Let's say we eliminated this first. Let's say we're looking at this one, and let's say this is left. This is right. This was right. So, and then both of them are pointing to the same one. And then we check again. 3 is not here, so that means it's probably after. So what we do is we move the left to this one, but left to this one, and now right is greater than left. Now right is less than left, so it's not there. And since this was the middle and it's greater, so now that means 3 will go before this, so right here on where the left was. And since both are pointing to the same one, this is also the middle. So if it's greater, yep. If it's greater, it will be after the middle. Oh, that makes sense. Because it's greater. No, that my previous assumption made sense. And if it's less than, it will be before the middle. It's just right. And this will only work whenever it comes out. So then, since I think you were targeted to return possible position times minus 1. Because you were supposed to return that value in a negative form, right? Does this make sense, or it's more confusing?
So I have a question about so you know how previously we were returning -1, right? And then because you know it's an index that's not found, right? So technically any number that's negative is going to be an index not found. So on the comment, right? I think that's line 3 at the top. Okay. It says return -1 if target is not found. Should that comment be updated to say return negative index if target is not found?
Return possible position in the negative form if value is not found.
So, and then the reason, right, for this, the reason why we would turn, so I mean, you could just return -1, say it's not found, but returning possible position times -1 gives you a better clue as to where it would be. Is that correct? If it were correct in the group of numbers.
Correct. This is an let me see. I'm still thinking through my logic. And anyone finds a flaw in my logic here, feel free to correct me.
So we have basically a left pointer and a right pointer. And so if the target is less in the middle.
Before this value, okay, that is the problem. So because it's not there, and it's not I might be after. So it is after this. So here it's the same. I just return the same value. Because it's not there. I'll just return the middle. That will make it so it's after. Because this is the thing, right? If it's after, middle plus, to keep it consistent. So this is before this value, or actually here, right? So this is wrong because if it's not there, it would be there. I just return the middle for in this case, because if I return the one before, this will be I would be saying the value should be after this, right? In this case, if I return this value here, if I return the 15th, I'm saying 48 should be after here, and after here is just 16, right? If the value, if we know the value is after, but it's not there, let's say here, right? Let's say we're checking this. And we know the value is 16. We know the value is after this, meaning it's this one. It's the next one after me. That's why. So in here is the next one. The value should be in the next one. If it's not found, you will find it. You should put it after me in this position. Make sense?
Yeah, I got why if the target is greater than the middle, that the middle plus 1 is the possible position. Can we go over one more time why if the target is less than the middle, why middle is the possible position?
And if it's before the middle, the value could be there. If that is the last option you have.
Oh, I see. It's the last option. That's why. So it's
either,
it's either the middle or the next one.
So like 48, we check 50, right? But it's not there. And then when we move right to this point, right becomes less than left, and then we get out of the loop, right? But if 48 is not here, it's not, this is 45, right? It would be after this one, but it's 50. So if 48 were to be inserted, it should be inserted here at this spot.
This kind of reminds me of when we were like when you're doing the example with the smaller set. Remember, with just like the two numbers, right? It's either going to be 2 or it's going to be 4.
Or it's going to be 4.
Yeah.
And then if you're looking for 3 in the middle, right?
Exactly.
If you're looking at the 4, you're going to say, oh, 3 should be here, but it's not. If you're looking at the 2, you're going to say, oh, 3 should be in the next spot, but it's not there. Yeah. If you're looking at the 2, you would say, oh, the target is greater, so it should be in the next spot, but it's not there. And if you're looking at the 4, you're going to say, oh, the target should be before me, but it's not there, so I should be the target. Make sense?
Does anyone have any questions about how to find what the possible position is and how to find the possible position of where the number or element we're looking for should be?
Yeah, and I will rename this to insertion position. I don't know.
I'm mostly trying to follow along, but I think I get what you guys are doing. I don't understand how you guys were collaborating on right minus middle times 1 though, or right equal middle times 1. I wasn't sure what that was about. I was a little confused with that.
So this one, so in 143. Is that the class?
143.
So they have an assignment where they have to implement. Are you in that class?
I'm in basic Python.
Oh, okay.
He's in 110, I think.
Okay. So
110.
So in that class, can I clear this? Can I just clear the whole thing?
Yeah, go ahead, sure.
Oh, maybe. Let's delete this. So what they are doing is that usually, if you don't find the value you're looking for, you return -1, or you return, if you're returning the value, you will return a null object or something. In their class, what the professor is asking is to return the possible position where that element will go. So if I were to insert 48, and I made a mess in there, huh? Oh, I erased the whole thing. Let's undo. Oh yeah, there you go. This works great. I love that. I love the undo button. So I made a mess in here. So if I am looking for 48, right? The last thing I did was I look at the 50, and 48 is not there. And I only have these two elements to look at, and I know 48 is not there. So I'm like, oh, I am supposed to look back in here, but I already eliminated this, so I know it's not there. So where would 48 go? It will go right here, right? It will go on position 16. So now you cannot return 16 because that would mean that you found the value at position 16. But what if I want to tell the user, if you want to insert 48 is not there. I couldn't find it. If you want to insert 48 in this array that is supposed to be kept sorted, you should insert it at position 16. There is where that value should go. So then, I can return -16, meaning I couldn't find it, but it should go there. That's why we return the possible position times -1 just to make it negative. Make sense?
Thanks for explaining that.
Yeah. So this is just, I mean, it's the same algorithm, just a little tweak to
just to make it a little bit easier.
And this is the reason. The reason for this is because they are implementing a data structure in Java where they're using an array and they are keeping everything sorted. And they're keeping everything sorted because of this reason, right? Because if the array is sorted, you can use binary search that works at complexity log base 2 of n, and you can take advantage of this speed. But if you want to, if you want to say, oh, is this value already in there? Oh, it's not. Where should I put it, right? You get where you should put it, and then you can just insert. You can, I don't know what the data structure API is like, what the interface is like, but you could say insert value 48 at position 16, right? Because it goes there, and this will keep the array sorted. And that's there's something in computer science, and this is I know it's a word that you will probably hear it a lot, and maybe not on these classes, but later on. class invariance. This means this no matter what you do, this should always hold. The array should always be sorted. That's a class invariance. And you have to make sure that whenever you do something in there, the array has to be sorted, because the rest of your data structure depends on that. And there are some data structures that are their specific function is to keep things sorted in a way, because that way you can take advantage of binary search. One of them is trees.
Mm-hmm. Also, I want to note something. Sometimes what Hari's talking about with class invariance, I've also heard it called preconditions, that, like if you go to some place like LeetCode or someplace, and they'll say, here are the preconditions for this problem. Like you'll never have a value less than, and you'll never have a negative number, or you'll never have whatever. You'll never have more than this many elements. And it tells you that you don't need to worry about those conditions because it wants you to focus on the other parts of the problem. So those things will always be true.
Oh yeah, and yeah, stop sharing my screen. But I remember there was a question. So I don't know if you guys still have time or if you want to call it a night.
I see. Is it Diana's question right there?
Yes, and I had done something. So I was playing with this. So what I have here, this is simple. So I'm using a library called matplotlib, and I am using another library called NumPy. I'm creating a range of values between 2 and 4096, and steps up to, just because. This is a print. This is just, I don't know why I put this here. Probably just to check my own logic. And then I am plotting the logarithm base 2 of each one of these values in the range. And this is the curve that you get, right? This is a logarithmic time complexity. This is linear. This is meaning the change on the time that it takes to compute something. It's proportional to the size of the array, the number of elements in that. It could be an array, it could be another type of data structure, but it's the complexity. It's proportional to the size of the set. It increases as the size of the set increases with the same proportion, just the same, what would you call this?
Elements, the number of
the same incline, the same. Yeah, you get what I'm saying.
Growth rate, right? The growth rate.
Yeah, the growth rate is the same. And this is quadratic. This is big O of n squared. And you see how it starts like kind of increasing slowly until it gets to a point that it's increasing so fast that the more elements you add, it will make your algorithm run very slow. It will make it run slow for a great amount of data. But you see this. You see how at the beginning, when you have a few elements, it takes 2, 4, 6 checks, and then it goes and it kind of flattens it. And you see, if it doubles, if the size of the number of elements doubles, it just takes just one more, and it that means this type of algorithms that are log of n are very efficient for a large for data sets with large number of elements. And when we would talk about time complexity, and this is one thing, right? You hear the name time complexity, and the time complexity, when we talk about time complexity, is that how the computational time increases as the number of elements you're computing increases, right? That's what time complexity means. In the I keep on saying, I'm thinking. So if we look at this algorithm right here, right, we are doing a few things. Each one of these things, it's a computation. Each one of these things, it's a computation. Each one of these. Let's say if we take all these different computations, these computations are very small, and we usually, when we talk about time complexity, we estimate that all these computations should be equal for every value. That's to simplify things, right? So we do 1, 2, 3 computations, and we do that as many times you fall in the loop, right? Every time you fall in the loop, a computation gets done. Meaning that if I check 1, 2, 3, 4 times, I have 32 elements, and I checked 5 times, right? So it's going to take 5 times greater than if I had 2 elements only, right? In linear time, it would take 32 times more. That's what the time complexity. And when we talk about big O, we're not talking about the exact time that the computation takes. We're talking about how it behaves according to these curves, right? It's never exact. It approximates one of these curves. That's why this +1 doesn't really matter. Let's say if you run a lot of computations and you take the time complexity and then you plot it, the curve will look like this. Does that make sense? And something I realized, we didn't even try this. We didn't even try this.
Oh, yeah, gotta test it.
Yeah.
Basically, what Hardy's saying is that the growth rate, the most important part is the general curve. So it doesn't have to be exact.
Curve. It doesn't have to be exact. I don't know. I'll just throw 1 in there for a good measure, and then I'm gonna say which value. Let me one that is not there. Let's do one that is in there first, and then I'm taking the array first. So it's what is this? Turn 0, 1, 2, 3. It should be 3. Oh, there's a flaw. There is a flaw. Huh? Yeah.
Oh yeah, so it was basically.
Of course, yeah. Of course, yeah. Of course, yeah.
But this is actually what Diana was referencing, I think, earlier.
Yeah.
About
There you go. There you go.
Indexes, the values of the indexes.
Yeah. The indexes. Yeah. It's just, anyways. But yeah, you see, we make mistakes, but the good thing is that we find them and we figure them out. Fine. And then one that is not there. For what is
What
not
about
there?
9? 9 or
9 is not there.
Mhm.
So it would be 0, 1, 2, 3, 4. Yeah, 9 should be here. That makes sense. Let's try another one. And I should be more descriptive in my I'm passing values that I know should be outside, just to test. And then I'm gonna do gonna do 19. This is just a test. So it's a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 100 should be 13 after. 0 should be at position 0 if it were there. And we'll move everything to the right. 19 should be right here. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it works.
Yay.
It looks like it works.
And the reason why for looking for 0 returns 0 instead of the negative form of possible position, because possible position is set to 0 already. So
yeah,
negative.
Yeah, it's just negative. There is no negative 0. It's this is and you know, this is a flaw in the algorithm, right? Because you don't know if you found 0 or it's like it's just but it's not there. Yeah, this is
That's a tricky one.
Ask Bill about this. What is the tricky one?
Well, because the possible position would be 0, but there actually is a number at the current index 0. So that's a good one.
Yeah. That's kind of funny. Yeah.
Does anyone have any questions about what's going on?
Oh, look at this. It's return mean value. Oh, but that is Java. So what would that be in Python? Like a very, very small number, right? Like a negative, like a big negative number. Does Python have anything like that? No, it's a good question.
That is a good question.
Yeah, but that is and the simple fix for that would be right here, right? We will check what possible position is, and if it's 0, we just return that some value there to make sure that's what we want. Any questions? Any?
And don't worry, honestly, I've seen binary search explained to me by Bill and now by Hardy, and I tried looking it up, and every time I look it up or have someone else explain it, it makes more it's like, oh
yeah
repetition basically. I've even written binary search, but it's like but anyways, the point is exposure practice always helps cement these things. Ooh, Rahil says negative sys period max int -1 according to Stack Overflow.
Sys max int? What is it?
It's in the chat. Negative
Max
max int -1 or -1.
Let's see. There's no attribute max int. Huh. That's odd. It doesn't. Oh well. We'll figure it out.
Yeah,
I'm just gonna add. yeah. It's. I will figure it out, but it doesn't really matter. There must be something in there, and yeah.
How's everyone feeling? Do they feel like they got a little bit of understanding?
I've seen a lot of this with JavaScript, just not with Python, so it's interesting to see it in an alternate version.
It does have it. Makes sense.
I totally agree, James. I actually feel like seeing it in Java and now Python, and I'm sure I'll see it in other languages.
Python kind of gives it a lot more of a simplicity than JavaScript, because JavaScript, everything's lying within the brackets, and it's hard to follow along.
So it's max size for Python 3. Max int is only in Python 2.
Oh, interesting.
That's interesting. So yeah, it says it's just max size, which is unsigned word, and since it is a sign multiplied by 2 plus 1.
Are Python 2 and 3 different versions or different types of the same?
So Python, they made a lot of changes to Python, and what they did is they were supporting Python 2 along this, at the same time they were developing Python 3, and Python 3 it's a big step from Python 2, right? To the point that some things are not compatible, and the problem with that is that there are a lot of programs, there's a lot of software written for Python 2, and people didn't want to switch because it usually, whenever you switch, if there's no compatibility, you have to change your code. So they had to support Python 2 at the same time. A lot of the distribution, Linux distribution, have switched to having Python 3 as the default right now. And it's I really like a lot of the improvements that they have done to Python 3. But at the same time, a lot of the things are different. And there's this compatibility issues, right? Things that work on Python 2 now don't work on Python 3. One simple example. In Python 2, you could do print like this, or you could do just print something like this. Now, this doesn't work on Python 3.
Oh, that's interesting.
Yeah, so this now in Python 3, you have to use the parentheses. Python 3 has some typing. You know how in Python, you don't have to declare what type of variable you're using. You do and just give it a name, right? It knows it's a string. So in Python 3, you can have types. You can have type. You can declare the type of your variable. And I don't remember the exact syntax right now since it's been a while. I don't use Python. But you can declare types, and they have a byte type and other things. And the idea is that sometimes when you're working with something that is lower level, you will want to have that ability. Yeah. And there's a whole lot of things. you know how in Python 2, sometimes you do import future? It was kind of, I always laugh when I saw this import future, right?
Yeah.
So import from the future. This is
That's so
importing.
funny. That's like time travel.
Yeah, time travel. Yeah. So this is importing features that were implemented on Python 3, but were not by default on Python 2, but you could get them importing from the future. I thought it was just the funniest thing ever. Yeah.
Not import version, import future.
Import
future. Yeah, right.
And if anyone's curious, I just posted in the chat a link to like an explanation on like naming for versions. So basically,
Okay.
I mean, there's other ones too, but basically,
yeah.
When the first numbers change, it usually means there's a lot of changes. It's a big change.
Yeah, it's a big change. Yeah, it's the subversion versus the big version, right?
Yeah.
Yeah, and one thing that I wanted to point out as well is that you see this. I don't know if you're familiar with Jupyter notebooks. Are you?
No, I haven't heard of it before. What is it?
So I am running this on VS Code, right?
Yeah, Virtual Studio.
Visual Studio Code. But you see how I can type in here, and I can get the results right there. This is like running interactive Python, but having your code in there already. And I can add comments, which I am going to do later. I can add comments are as marked down in here. So I can say binary search. I can write my comment. So I can write my comments there, and I can write my code, and it runs. And all you need to do is, there is an extension, Jupyter. So there's this extension. You can install this extension, and that makes it so if your file has the extension IPYNB, the Jupyter notebook, basically, it just works. It just works, and I love this.
So Rahil says, Hardy, can you go over again why we need to do possible position equals middle plus 1 if target is greater than our middle index, but we just say possible position equals middle otherwise?
Yeah, right. Okay. So back to my mess. Oh God. How can I clean this up? Let me see if I can. My tablet died. Okay. So let's take again the 48, right? We were looking through it. In the end, we were looking in this section right here. And the last value we were looking at was 16 because 16 was the middle right here. Right? But we just have two values. And this is left. And this is...
Oh, Hardy, I think you need to share your screen.
Oh, sorry. I didn't realize. Oh, sorry. Anyway, so I said we're looking for 48. The last thing we checked was 16, right? Because that was the middle right here. And then this was left and this was right. But when we look at the 16, we realize, oh, 48 is not there. 48 should be back here, right? So then I take this right, and I put the right here. And that makes it so I get out of the loop, right? But now what I realize is that where should 48 be? 48 should be right here, right? Am I correct?
Yeah.
Yeah, 48 should be right here. So in that case, I'm saying that if 48, if I realize the target is less than the value I'm looking at, the value should be there actually, right? That one makes sense. Now the other case is, and I took an example just out of nowhere because I don't want to go through the whole thing and see if it works. So let's say I am looking for 15, and let's say that I only have these two elements right here, 14 and 18. This is left, and this is right. $15 is not here, but 15 should be after, right? I am looking at 14. 14 is also the middle. If 15 is not here, it should be after me. And then what I do is, okay, since I am moving, so I move my left to here. Actually, that's what will happen with our algorithm. And then again, 15 is not there, and then it will look back. So this doesn't work as an example. It will only work if this were the only value, and that could be the case. This is the only value, and this is left, and this is right. And we're looking for 15, and we say, well, 15 is not here. It should be after. But this is the only option, right? So if 15 is after me, if the value, the target value I'm looking for, is after the value I am looking at, it should be in the next spot. It should be in the next pocket, right? Hello.
I really like the example of the really small set, because like, you know, sometimes it's easier to visualize with really small sets.
I know. I just my tablet. Oh no, it's back. It's alive.
Yay!
It's just very low on battery. So yeah, a very small set, and then let's say we have what 4. I will do 4, and I will do 8. And let's say I am going to look for.
Let's look for 5.
I'm going to do 3. And I am going to look for number 10.
Oh, yeah, that's a good number.
Here. So I look in here first because it's the middle. And this first, this is left, this is right? So now it's not there, it should be after. Again, we're falling into the same trap. No, this is not a good one. Because I'm going to look at the next one, and that's going to be before. So I'm going to say we're looking for 6 right there, because that would work. So this is left, 4 is left, this is 12 is right. We look at the middle, it's not there, right? So we discard this whole thing. So all we have left is 4, and 4 is left, and 4 is also right, and amazingly, it's also the middle. It has different roles at the same time. So and we look at 4 and we say it's 6 there. No, it's not there. So now it must be after, right? By our algorithm, then left should move to here now. That makes it so left is greater than right, and we get out, right? But where should 6 be? I am the middle, and 6 should be after me, right? So if this is index 0, this is index 1, so 6 should be at index 1 if it were in the array, right? So I just return, because middle is 0. Middle plus 1. That would take me to the next one. That's what we had there.
Yay! So it looks like that made sense to people, made sense to everyone. And oh, Diana asked before she left if she could connect with you, Hardy.
Oh yes, sure. Yeah.
I was actually thinking, Hardy. So on the pages for us on the on our Bevy site, I noticed you don't have your LinkedIn information on there. So
oh really?
Yeah, on the Bevy one.
Okay. Okay. I'll just update that.
But she's also in the Discord, so no big deal.
Yeah, this was a lengthy thing. Well, anyway, this is good. It's good.
That was good. It was good for me to have a review, because even though I wrote one, it's like I feel like now that I've seen it for like the 3rd or 4th or 5th time, it's really like like sinking deeper in each time, basically.
Yeah.
I know I'm gonna have to expect this in my next class, so it's nice having an introduction to the problem, because I already know how I'm gonna have to think about it now. I was gonna ask if you didn't mind, would it be all right if I were to copy the code?
Oh, I'm going to put this in the I don't know.
In the chat?
Kristen, are we going to create a GitHub account for this?
Yes. So there's a club GitHub, and we can make a repo just for all of the Jupyter notebooks that are created from these data structured algorithm events. So that way it'd be easy for people to reference the code that was written during the event.
Okay, that works.
Okay, so yeah, I'm just gonna I'm going to write some comments in there, and then I'll upload the code, and it's just a Jupyter notebook file, and yeah, you can play with it.
Perfect.
Or improve it. Right?
I don't know if I could do that. It looks pretty good already.
Yeah, and it's just the one thing, and this is what I love about this algorithm. It's simple. It's elegant, right? It's just this. it's very efficient, but it's simple.
I agree. I tend to put a little bit too much work into my code when the code is supposed to do the work for me. Doing many lines of things I don't need. So I like seeing simple things like this. It helps me realize how I'm supposed to be thinking when I'm developing, you know.
Yeah.
More simplest, more easy.
And
So thanks for coming, by the way. Thanks for hanging out with me.
Lots of great questions. And like James, you had mentioned learning some of these things in JavaScript, but so I learned them first in Java, but actually Python is recommended for learning these things because the syntax is so similar. It's so simple.
Mm-hmm.
So you really get the concept.
It's true.
So Ray, were you really working on it while we were doing it live?
I know, I saw that.
Oh god. Oh my god. Two screens is very convenient. No, but and this on how to return the possible position is something that I didn't know. The algorithm usually doesn't have this, right? We just came up with this right now on the fly. And it's great. And usually what you want to do, you want to draw the problem and follow through it, by hand. And then you will see, you see how at the beginning, for returning the possible position, I was wrong. But when I double checked myself, I was like, oh, yeah, no, this is not right. And I realized and I corrected. Yeah. Anyways, I'm gonna sign off, if you don't mind.
Thank you so much for the demonstration.
Thank you guys for coming. Yay! First data structure and algorithms event for our little club chapter.
Yeah, we should keep it going.